Here is how the model checking algorithm proceeds. As a first step, we will construct an automaton for the negation of our formula phi. In general, we uniformly associate an automaton, denoted aut psi, to each formula psi. So following this notation, we actually construct aut not phi. As is often the case, the automata we'll consider will operate by accepting words. The words we consider will be infinite sequences of atom sets, of the kind produced by labeling infinite sequences of states. As usual, the set of accepted words of an automaton will form its accepted language. Now, the accepted language of the automaton aut psi, associated to a formula psi, will be shown to satisfy the following important property. Given any labeling, the atom set traces of sequences pi that the formula satisfies are exactly the words that the automaton accepts. This is expressed by this if and only if statement. Pi satisfies psi if and only if the atom set trace of pi through L is accepted by aut psi. In particular, aut not phi accepts precisely the atom set traces of sequences that do not satisfy phi. Okay, so after this step, we have the automaton aut not phi associated to a formula phi. In step 2, we combine the automaton aut not phi with the LTS M and its chosen state as 0. We will obtain a product of the two, denoted like this: M as 0 times aut not phi. The language accepted by the product automaton is essentially an intersection between what aut not phi accepts, meaning what phi does not satisfy, and the valid paths from S0 in M. Namely, its accepted words will be exactly the atom set traces that are given by paths in M that start in S0 and do not satisfy phi. Okay, so we have this if and only if statement. Pi, it's a path in M starting in S0 and not satisfying phi, if and only if its atom set trace through L is accepted by the product automaton. Finally, in step 3, we check if the language of the product automaton is empty. If it is empty, this means that we are not able to find any paths starting in S0 and not satisfying phi. So we're not able to find any paths with this property. In other words, all paths starting in S0 do satisfy phi. So we can conclude that M in S0 satisfies phi, because this is the definition of M satisfying phi in S0. All M's paths starting in S0 satisfy phi. Otherwise, if the accepted language is non-empty, we obtain such a path. We obtain pi, a path in M starting in S0 and not satisfying phi. So we can conclude that M in S0 does not satisfy phi. Okay, this was the high-level description of what's going on in the model checking algorithm. For step 1, we have not yet discussed what automata we will use, how we build such an automaton from a formula, and of course, why is this construction correct? Why does it fulfill its required property, which connects it with the original formula, that satisfaction of a formula psi is equivalent to acceptance in the associated automaton, aut psi. For step 2, we of course must define product automata and we must show that they satisfy the required property, that acceptance in this automaton, in the product automaton, captures both formula non-satisfaction and the fact that the considered sequence is a path in the LTS. Finally, for step 3, we must show how the check of emptiness is done algorithmically. And of course, here too, we must show why our conclusions are correct. Why do emptiness imply satisfaction and non-emptiness imply lack of satisfaction? In other words, why is emptiness in the product automaton equivalent to satisfaction? A note on the algorithmic aspect. Of course, not only step 3, but also the other 2 steps must be algorithmic. However, for steps 1 and 2, the algorithmic aspect will be obvious. It will be clear that both the translation from formula to automata and the construction of the product automata are computable steps, which you can implement in your favorite programming language. For step 3, this will not be clear before we describe an emptiness criterion. In what follows, we'll answer the questions shown in red.